Hello, everybody. My name is Ali Muhsan. I'm a PhD student in materials engineering at the University of Dayton. The title of the research is the Numerical Study of the Electrochemical Exfoliation of Graphite by Ali Muhsan and Khalid Labdi. In this study, we simulated the electrochemical exfoliation of graphite to show the main process of electrochemical exfoliation, intercalation, and exfoliation. A numerical study of the electrochemical exfoliation of graphite was carried out using Thomson multiphysics. The homemade graphene oxide was characterized using optical microscope, scanning electron microscope, Raman spectroscopy, and X-ray diffraction techniques. The numerical study showed that the concentration of silvite anions was transported through a graphite rod in the range 9.77 multiplied by 10 power minus 7 to 4.8 multiplied by 10 power minus 5 mole over meter cubic. And the stresses distribution, which resulted from the silvite anions interaction along the graphite rod in the range 3.43 multiplied by 10 minus 8 to 5.77 multiplied by 10 power minus 7 in Newton over meter square. A graphene, a two-dimensional honeycomb sp2 carbon lattice, shows a potential use in the next generation of the electronic devices, composite material, energy storage, and conversion, drug delivery, sensors, and catalysis due to its extraordinary properties of graphene or graphene oxide. Since the graphene discovery in 2004, many fabrication methods were explored. A graphene can be prepared by micromechanical exfoliation, epithelial growth, chemical vapor deposition, solvent and or surfactant assisted liquid phase exfoliation of graphite, and thermal or chemical reduction of graphene oxide. The electrochemical exfoliation of graphite has attracted specific attention due to its simplicity, fast, controllable, and environmentally friendly in producing high quality graphene. The electrochemical exfoliation process involved shear deformation of a graphite electrode by applying an electrical potential, either anodic polarization to oxidize the graphite rod, or to produce graphene oxide, or cathodic polarization to obtain graphene, then allow the cations or anions to intercalate between graphene layers to form graphite intercalated compounds. The electrolyte played a major role in the electrochemical exfoliation process due to its influence on the composition, structure, and properties of resulting graphene sheet. Different kinds of electrolytes have been used, including ionic liquids, high molecular polymer, polar solvent, surfactant, and inorganic solution. Among them, sulfuric acid solution has been more frequently investigated because of its high yield, which is essential for the practical use of graphene. Quality of graphene is strongly dependent on the potential applied, as well as by the electrolyte employed. In this slide, we will present previous work done by other research. Abdul Qadir et al. Prepared graphene via cathodic exfoliation of graphite in dimethyl silver oxide containing lithium and 3-ethyl ammonium. They obtained few layers of graphene with a diameter ranging from 1 to 20 micrometer without using sonication or centrifugation process. Another work done by Ambrosi and Bomera studied electrochemical exfoliation of graphite using 3 different electrolytes: sulfuric acid, sodium sulfide, and lithium perchloride. They reported that a graphene produced in sulfuric acid had higher density of defects than other electrolytes. However, lithium perchloride seems very suitable electrolyte to prepare graphene oxide because of a high amount of oxygen functionalities the graphene oxide can be used as additives for the fabrication of polymer-based nano composites. Huang et al. Utilized two steps of electrochemical exfoliation using sodium hydroxide to expand the graphite foil and sulfuric acid solution for the exfoliation. They reported that the two steps electrochemical exfoliation produced high-quality graphene. And another work done by Kakai and Hensport investigated the role of acetyl trimethyl ammonium bromide as an electrolyte on the mechanism of the electrochemical exfoliation of graphite. They reported that the CTAB intercalate into the graphite rod, then followed by oxidation process to produce graphene. And another work done by Shandy et al. Studied electrochemical exfoliation of graphite by shear assisting to exfoliate graphene and simulated this process using COMSOL multiphysics. They stated that the shear rate played a main role on the yield, thickness, and the quality of exfoliated graphene. And another work done by Bobby Sheva et al. Simulated the graphene nanoplatelets exfoliation via ultrasonication process using Gaussian and universal force field. They reported that a non-resonant locking mechanism involving surfactant molecules is shown to be a feasible exfoliation mechanism through direct ultrasonication. Young and Leo studied the mechanism of liquid exfoliation of graphene using molecular dynamics. They reported that the sliding away mechanism is played a main role for liquid exfoliation process because the surfactant graphene interaction is maximized and which is critical to the separation process. And another work done by Shou et al. Studied exfoliation mechanism of graphite for modified hammer methods. And they stated that the layer spacing of a graphene sheet, 3.334 angstrom, calculated by molecular dynamics simulations, coincided with the X-ray diffraction results. The experimental part, the electrochemical exfoliation cell consisted of a graphite rod, which used as the working electrode, and the platinum wire worked as the counter electrode, and the electrolyte used in this study is 0.1 molar diluted sulfuric acid. The anodic exfoliation of graphite carried out by using power supply through applying an electrical potential to the graphite rod tenfold at room temperature. Anodic potential oxidized the graphite rod and allowed for sulfide anions to intercalate through interlayer spacing of graphite to exfoliate the graphene oxide. The exfoliated graphene collected and washed using deionized water many times to remove the sulfide anions throughout vacuum filtration. Then the collected exfoliated graphene dried in oven at 60 Celsius degree. Actually, the electrochemical exfoliation setup, as shown in figure 1, the experimental setup for the electrochemical exfoliation, as shown in this figure, the power supply connected to the graphite rod and to the platinum wire in the presence of the electrolyte, which is diluted sulfuric acid. A numerical study, COMSOL multiphysics 5 used to simulate the electrochemical exfoliation of graphite. We used a three-dimensional model to build the electrochemical exfoliation cell. The dimension of the graphite rod domain, 2 micron radius and 4 micron the height of the graphite domain, and the diluted sulfuric acid domain, 4 micron radius and 5 micron the height of sulfuric acid domain. The physics was used to simulate the electrochemical exfoliation, transport of diluted species, and the fluid structure interaction physics to simulate the intercalation and exfoliation process. The equation used to model the electrochemical exfoliation of graphene based on the diffusion and fluid structure interaction. Actually, in this study, it's a time-dependent study, and also the migration of the sulfide anions to graphite rod under an electrical field. The flow in this study was considered as incompressible, and it is represented by the equations 1 to 2. As we see here in equation 1 to 2, actually we define the parameters. Consideration of sulfide anions, diffusion coefficient of sulfide anions, and also we define the velocity, and also we define the electrical potential applied to the cell, and the mobility of the sulfide anions. And also the equations 3 to 5 represented the fluid structure interaction. We see here, we define the parameters like raw density, and U is the velocity of the sulfide anions, and mu is the dynamic viscosity of sulfide anions, and also Poisson ratio of graphite. As indicated in figure 2, the mesh related system, the system meshed by using physics controlled meshing to solve the equations numerically. Characterization tools, graphite and graphene oxide were characterized by using optical microscopy, scanning electron microscopy, X-ray diffraction, and Raman spectroscopy. Results and discussion. Figure 3 shows us the photographs of the graphite electrode before and during the electrochemical exfoliation process. As we see here in this figure, in figure 3A, we see here the graphite rod and platinum wire before applying electrical potential. Well, we see here in figure 3B and 3C the graphite rod during the electrochemical exfoliation. Allowed to sulfide anions intercalated at edge and the defect sites of graphite, then followed by reaction of sulfide anions to release silver dioxide, which leads to graphite exfoliation. Actually, this process of oxidation and radiation occurs simultaneously during the electrochemical exfoliation process. Figure 4 shows the graphite rod before and after exfoliation process using optical microscope. As shown in figure 4B, the influence of the electrochemical exfoliation on the graphite rod because of the intercalation of sulfide ions. Figure 5 shows the SEM image of the graphite rod and for exfoliated graphene oxide. As shown in this figure, as shown in figure 5A, the very compacted carbon stacks, and conversely, the graphene oxide is made of well-spaced layer, which the interlayer spacing is in the 100 nanometer scale, and which show us the rule of the sulfide anions intercalated between graphene sheets. The crystal structure of the graphite and the exfoliated graphene oxide were analyzed by conducting X-ray diffraction. Figure 6 shows us the XRD patterns for the graphite powder exfoliated graphene oxide. As indicated in figure 6, the graphite powder had sharp peak at 26.4 degree with D spacing 3.37 angstrom. Also, the pattern for other peaks are different to theta. As shown in figure 6, the exfoliated graphene oxide had the same graphite pattern and appearing a peak at 10.8 with the D spacing 8.19 angstrom due to the presence of hydroxyl, epoxy, and carboxyl groups. Figure 7 illustrated the Raman spectra for graphite and exfoliated graphene oxide. The showed D, G, and 2D bands. The D peak originates from the breathing mode of 6 atoms and requires a defect for activation. Therefore, the intensity of the D peak, this D peak, the intensity of the D peak depends on the disorder of the graphene. We see here in this figure, this D peak, and this is G peak, and this is 2D peak, and this peak is G. The 2D peak is the second order of the D peak, and the shape of the 2D peak to the different thickness of few layers of graphene sheets according to the Ferrari et al. The evaluation of the evaluation of the 2D peak is a clear indication of the structural transformation from graphite to graphene heterostructures, ctrochemical exfoliation. The G peak represents the E2G phonons vibration mode in the center of the Brioni zone of carbon atom. The graphene oxide spectrum shows shifting of the main peaks to G and 2D and appearing a new G band at 2910 centimeter power minus 1 because of the exfoliation process. The intensity ratio of ID to IG of graphite and exfoliated graphene oxide was 0.46, 1.49 respectively. The covering equation were solved numerically using finite element method for the mesh system. Of the simulation showed that the sulfide anions transported and interacted with the graphite rod to show the mechanism of the electrochemical exfoliation numerically. Figure 8 shows us the contours and slices of sulfide anions concentration through the graphite rod in the range 9.77 multiplied by 10 power minus 7 to 4.85 multiplied by 10 power minus 5 mole over meter cubic, which indicated the intercalation of sulfide anions into graphite rod to form graphitic intercalated compounds. The concentration gradient of sulfide anions through graphite rod is represented the intercalation of sulfide anions. The result of fluid structure interaction physics showed that the interaction of sulfide anions along the graphite rod. As shown in figure 9, the stresses applied and the velocity field of sulfide anions around the graphite rod. We see here in this figure the stresses around the graphite rod and also the velocity field of the sulfide anions. The stresses gradient along graphite rod is in the range 3.43 multiplied by 10 power minus 8 to 5.77 multiplied by 10 power minus 7 in Newton over meter square, which is a properized stresses to break down the weak van der Waals between the graphene sheets to exfoliate graphite. In the previous work, which is done by Shendi et al., studied Comsol multiphysics to simulate the exfoliation process of graphite, and they showed that the shear rate played a main role in the exfoliation process. In this study, we presented the full description of the electrochemical exfoliation of graphite numerically and the role of electrolyte in this process. The validation of this simulation is indicated. Show the photographs of graphite rod during the electrochemical exfoliation, which totally verified this. Prepared using an anodically electrochemical exfoliation technique. XRD graphene oxide indicated appearing a peak at 2 theta, 10.8 degree, with D spacing 8.19 angstrom, which is related to the graphene oxide. Raman spectrum showed that the intensity ratio I2D over IG 0.22. Therefore, the prepared graphene oxide consisted of few layers with a crystallized size 22.8 nanometer. The numerical study indicated the concentration gradient of sulfide anions throughout A graphite rod is in the range 9.77 multiplied by 10 power minus 7 to 4.85 multiplied by 10 power minus 5 mole over meter cubic. Also, it showed that the magnitude of stresses applied along the graphite rod is between 3.43 multiplied by 10 power minus 8 to 5.77 multiplied by 10 power minus 7 Newton over meter square. So these stresses along graphite rod are proper to break down the weak van der Waals band to exfoliate graphite. Thank you for listening.